Hello viewers, welcome to this next lecture of our series of lectures on spectroscopy. Today I wish to take up rotational spectrum, and this first part of our lecture, two lectures on rotational spectrum, I will take up the origin and nature of spectrum. And this session has been planned as follows. As we have been doing all these times, that we will try to review what we have done in the previous sessions. Thereafter, we will talk about what exactly is the meaning of rotational spectrum or what is rotational spectroscopy. Thereafter, we will see that how do we resolve rotational motion of a molecule. Then we come down to a rigid rotor, that is the way our diatomic molecules are modeled. We will understand what is the meaning of a rigid rotor as a model of diatomic molecules. In this context, we will come down to what is the kind of energy expression we get there, the corresponding energy level diagram, and then what is the kind of a prerequisite for any rotational spectrum to be observed. What is the requirement for a molecule to be able to give a rotational spectrum, and then thereafter we will learn about the selection rules. We have talked about selection rules earlier also, you will recall, and then we will talk about the spectrum. How does a rotational spectrum look like? What does it mean? And then towards the end, we will try to sum up what we have done in today's session. Let us try to recall what we have done in the previous sessions. You will recall that we started with defining what is spectroscopy, and then we outlined its scope, and we will recall that we talked about spectroscopy to be the study of interaction of radiation and matter, and its usage in a variety of things over there. Thereafter, in this context, we talked about the nature and characteristics of EM radiation. This was followed by recalling what is the nature of atoms and molecule, basic the energy level diagram of atoms and molecules and things like that. Thereafter, we came down to having defined what is EM radiation, what is a molecule, how does it look like, what are the energy levels over there. Then we talked about what is the type of interactions possible between EM radiation and the matter, and what are the prerequisites or necessary conditions for such an interaction to take place. This was followed by the types and characteristics of a spectrum. That means, we all recall that a spectrum, there can be an absorption spectrum, emission spectrum, or a scattering spectrum kind of a thing. And thereafter, in the terms of characteristics, we talked about the position of the signal and the width of the signal and intensity of the signal. So, there are three things we talked about over there. And then towards the end, we have talked about basically we described the basic features of instrumentation, because to be able to understand, to be able to gauge what kind of interactions taking place between a molecule and the radiation, we have to have some means of doing that. In that context, we talked about what kind of instruments are used for the purpose. Okay. So, having done that, let us get going with today's session. Let us try to see what is rotational spectroscopy. Rotational spectroscopy basically is a study of the consequence of interaction of electromagnetic radiation in the microwave region with the molecules. You will recall when we defined spectroscopy, we said it is the interaction of radiation and matter. That is a broad term. But when the radiation happens to be in the microwave region and that interacts with the molecule, so that study basically comes in the purview of our rotational spectroscopy. This is so because the microwave radiations have got energy sufficient enough to cause transitions amongst the rotational energy levels of the molecule. That is why it is called as rotational spectroscopy. Further, since we are using microwave radiations for the purpose, this also is called as microwave spectroscopy. So, the terms are used interchangeably, and typically such a spectrum which comes as a consequence of interaction of microwave radiation and molecules is called as a rotational spectrum. And this spectrum is used to determine variety of things there. First of all, it can be used to find out the bond lengths of simple molecules or even the shapes of small molecules. We will talk about the size of the molecule at a later stage, and then it can be even used to find out the isotopic masses, and then even the isotopic abundances can be worked out on the basis of the rotational spectrum we get from a molecule, and even the dipole moment measurements can be determined from the rotational spectrum. Okay. So, that is about our rotational spectrum. Now, let us see how do we have said, okay, the spectrum is going to be there and it is going to give me so much of things there, but what exactly, how do I get a spectrum, what is the basis, what is the origin of spectrum to be there. Let us see, we know that molecules and their motions are three-dimensional, because we know that all molecules are three-dimensional, and when they move, so they are moving in 3 dimensions and they execute variety of motions. One is a translation motion, molecule is here, it is moving, or it undergoes rotation, or it undergoes vibration. There are variety of motions, we talked about that earlier too. Now, these motions are in 3 dimensions and these are quite complex, especially the rotational motion of molecule is quite complex, and it becomes convenient to talk about that if you are able to resolve that rotational motion of the molecule in terms of 3 components. They are called as a rotational components. You take a molecule and think of 3 principal axes, the 3 axes, x axis, y axis, z axis, and put a molecule over there, let the center of mass of the molecule be at the origin, and then this motion of the molecule can be resolved in terms of what is the motion, the rotation component along x axis, along y axis or z axis, and so on and so forth, but they are typically called as A, B and C axis. So, accordingly the molecule has got 3 principal moments of inertia along the 3 axes. I am sure that you all know from your basic physics, the school physics, what does a moment of inertia mean. Now, the moments of inertia along the 3 axes, I said A axis, B axis and C axis, which typically can be taken as the x axis, y axis and z axis, they are called as, they are labeled as or designated as IA, IB and IC respectively. Now, the magnitude of these moments of inertia are used to classify molecules. What does it mean is, now if I have a molecule, the molecule is rotating, so depending on what are the components, what is the value of IA, is it 0 or non-zero, is it more or less, so that is used to classify. Let us take some examples to see here. Typically, if I look at linear molecules, for linear molecules, if I try to see, I find that for linear molecule IA is equal to 0. Let us understand what does it mean. Suppose I have got a diatomic molecule, let me just take pen as my example here. So, this is one the tip is for say small atom here, and this side of the molecule, this is a larger atom over here. Now, if I take this molecule and this is my A axis, this is my B axis, this is my C axis. Okay. Now, if I take this molecule and rotate on the A axis itself, on the x axis so to say, so there is no change in the moment of inertia, because if you look at the molecule, so there is an atom here, another atom here, and as long as I am moving like this, nothing is changing, because atom is uniform, it is spherical. So, when I move a sphere along this axis, nothing is changing, the moment of inertia is 0 here. As against that, if I take the molecule and rotate say like this, I will find that one atom is smaller, one is larger. So, when the 2 masses which are not same, when they are moving, they are going to cause some value of the IB. Similarly, if I move along the z axis, I am going to have value of IC. Okay. So, since the molecule is linear, along A axis there is no moment of inertia, along B and C axis the moment of inertia will be equal to each other. So, on that basis we talk about the molecule to be a linear molecule. Now, if I take a molecule of this kind, say trichloro or trifluoromethane, the molecules of this kind, if I try to resolve the rotational motion of this molecule, I will find that, so IA is non-zero and IB will be equal to IC, which will not be equal to IA, because that is the nature of molecule is such, because it loses symmetry on one side. So, such molecules are called as symmetric tops. If I move further, if I look at a molecule like say methane molecule is highly symmetric. So, irrespective of which direction I try to look at, say along A axis, B axis or C axis, I will find the moments of inertia are going to be equal. So, such is a symmetric molecule, it is called as a spherical top molecule. And lastly, we have got asymmetric top molecules, say a molecule like water. In such cases, none of the inertias are going to be equal to each other. So, IA is not equal to IB, is not equal to IC. Such molecules are designated as asymmetric top molecules. So, having seen how do we kind of classify molecules on the basis of the respective moments of inertia, let us get going and try to see how do we model the rotational motion of a diatomic molecule. Let us look at a molecule like this. So, you have got a diatomic molecule and we know that there are going to be 2 atoms. Let us take atom 1 of mass m1, atom 2 of mass m2, and the distance between the 2, the so called bond length, as capital R. Now, we know that any molecule which is diatomic molecule is linear by default, because any 2 points will make a line. And what we do is, typically if you recall that when we talked about quantum mechanical systems, model system earlier, particle 1 dimension box, 2 dimension box and so on and so forth, what we do is we try to start with things which may not be the reality things, but we try to make things simpler to begin with, so that we can handle the equations. So, here also what we do is we assume, we start with the assumption that our molecule is rigid. What it means is that the two atoms, atom 1 and atom 2, are held together by the bond which is rigid. We know that it is not true. We know that because molecules do vibrate. If it is rigid, it cannot vibrate. We know that molecules vibrate. We make an assumption here. We start with it as a model, so that the quantum mechanical treatment becomes simple, and thereafter we are able to visualize the significance of the expression over there. So, what we do is we take a molecule and define terms like, so this is my center of mass of the molecule, R1 is the distance of the atom 1 from the center of mass, and R2 is the distance of atom 2 from the center of mass. Okay. So, that is the kind of system I am talking about, and R, I repeat, is the bond length, the distance between the two nuclei, the nuclei of the two atoms atom 1 and atom 2. To understand what you are going to get from here, the quantum mechanical expressions and the energy level diagram and all, we need to use a term called as moment of inertia, which I am sure that we know from your basic school physics. Let us see how do we try to find out the expression for moment of inertia for a diatomic molecule. So, I will just quickly go through a small derivation which you can do on your own. It is a very trivial kind of a derivation. So, we have bond length defined as to be equal to the sum of the two distances R1 and R2, the distance of atom 1 and atom 2 from the center of mass, and we know that our law of moment, the first law of moment says that m1 R1 to be equal to m2 R2, and we also know that the moment of inertia is defined as m1 R1 square plus m2 R2 square, and therefore, there are more systems, more atoms there, we will put it as it is basically sigma mi Ri square. If I do a little of manipulation here, little of simplification, what we come across is that we come down to an expression that I moment of inertia to be equal to m1 m2, the masses of the two atoms, and the sum of their masses, into r square. R square is the bond distance or the bond length, and the expression here m1 m2 by m1 by m2 m1 m2 by m1 plus m2 is called as a reduced mass. I am sure that you are familiar with this term. So, what I am basically interested in is that I is equal to mu r square. This is an important expression which I am going to use thereafter. So, that is why I spent little time on trying to make a small effort to derive an expression for the moment of inertia. Okay. So, having done that, let us move further. If I take a rigid rotor, that means a diatomic molecule, and try to analyze this, try to handle this system in terms of our quantum mechanical approach, which we learnt earlier, wherein for every system we try to formulate Schrodinger wave equation and then solve it and then try to get some wave function and energy expression. You have done that a number of times earlier. So, I am sure that you appreciate that, and you are convinced about it that when I do such a thing, I am going to come across an energy expression. In this case, we are not going to solve the problem because little elaborate and it is not required. But what we need to know is that if I take if I try to handle the problem of rigid rotor in terms of quantum mechanical approach, what I will be getting is I will be getting an expression of the kind which reads at E j to be equal to h square by 8 pi square I j into j plus 1 joules. What it means is that I am getting energy expression which says that energy is quantized and j happens to be the rotational quantum number. And also you will see that why did we spend time on working out an expression for moment of inertia, because that is going to figure into this energy expression. That is why we spend time on that. So, operationally speaking, when we take a microwave spectrum, typically our x axis happens to be in terms of wave numbers. Wave number is a unit which is used for the purpose. So, we will try to convert this expression E j, we know that E j we can define this small that epsilon j or small E j to be equal to E j by h c, where E j is the energy in terms of joules. If you divide by h c, that comes out into centimeter inverse. Basically, I am just converting the units from joules to centimeter inverse. So, for microwave spectroscopy, normally this is expression which is used more often. So, what we get is E j to be equal to h by 8 pi square I c, and I said earlier J is a rotational quantum number. Once we get this expression, what does it mean? What does it mean is, before we go further, let's try to make the expression little simple. We had Ej to be equal to h by pi square I c j into j plus 1. Let's try to see that the terms here h, 8, pi square I, the moment of inertia for a given molecule is a constant, c is a constant. So, all these terms here happen to be constant here. So, this whole thing is a constant, we call it as B prime or B, sorry, we will call it as B bar. B bar is called as the rotational constant. Okay. So, our expression now becomes very simple, that our Ej is equal to the rotational constant, that is B bar j into j plus 1 centimeter inverse. So, having learnt about the energy expression for a rigid rotor, let us see what kind of energy level diagram we get from this expression. So, we have got Ej to be equal to B bar j into j plus 1, and if I put different values of j, let us see what kind of an expression we get, what kind of a diagram we get. So, we see that for j is equal to 0, if I put j is equal to 0, energy will come out to be 0, that is we got 0 energy here. And if I keep on doing that, what you find is that we got different energy levels, and the energy levels are at 0, 2, 6, 12, 20, 30 and so on and so forth in terms of B bar unit, the rotational constant units. Now, what you see is if you just try to analyze this expression, we find that first level of course that when j is equal to 0, energy is 0, which implies that the molecule does not rotate, that is fine. Now, when I come to j is equal to 1, the energy happens to be 2 B prime, 2 B bar, and if I just go further, it is 6, then 12, 20, what you find is as j increases, the energy levels are getting farther and farther. That is one interesting observation we have about it. We will talk more about it as we proceed further. Now, let us go having seen what is energy expression, what is energy level diagram. So, the next thing is let us try to understand that what is the kind of a prerequisite for a molecule to show rotational spectrum, because it is not that any molecule you take and you interact with microwave radiation, you will get rotational spectrum. It is not true. So, there is some kind of a prerequisite there, and the prerequisite happens to be that the molecule must possess a permanent dipole moment. What it means that, now suppose I take any homonuclear diatomic molecule, such molecules like say hydrogen, nitrogen, they will not give rotational spectrum, whereas the molecules say heteronuclear molecules say like HCl, HBr, carbon monoxide etc., they will be giving rotational spectrum. That means the basic thing is that the molecules must be polar for it to be able to give a rotational spectrum. Now, let us see why so. Let us take an example of say HCl molecule. What happens is, if I take say molecule of HCl, so you see that there is a polarity in this case. So, as this molecule tumbles, as it rotates, we find that its dipole moment changes, and what you get is, we get an oscillated dipole moment. As a molecule rotates, I am getting an oscillation in the dipole moment, and this oscillated dipole moment of the molecule interacts with the electric component of the microwave radiation. So, we have radiation coming there, we have molecule which is tumbling. So, this is generating an oscillated dipole, and radiation is coming with an oscillatory electrical component of the field, the radiation. So, the two will interact. So, this dipole moment provides a mechanism for this interaction to take place, and in such cases only we will be getting the rotational spectrum, whereas if I take a homonuclear molecule, in such a case there will not be any spectrum observed. Okay. The next thing which we need to talk about is that what is the selection rule. The selection rule for rigid rotor happens to be very simple, that is delta j is equal to plus minus 1, which means that the rotational quantum number can change only by 1 unit. That means you can have say level 0 to 1 transition, or 1 to 2, 2 to 3 and so on and so forth, or the reverse order, say 3 to 2, 2 to 1 or 1 to 0. So, it can change only by a unit. Okay. Now, let us see what are the possible transitions here. We can see that as I just mentioned, that delta j is equal to plus 1 or minus 1. I am showing expressions, the transitions for delta j to be equal to plus 1. If that be so, the first transition I will observe will be from 0 to 1. Next will be from 1 to 2, 2 to 3, 3 to 4 and so on and so forth. And if these transitions are there, the resulting spectrum will be something of this kind. That means this is my 0. So, the first transition will be at 2b or 2b bar, where means that is a difference between, that is a delta E value between the first two energy levels. So, from 2b bar, so 0 to 2, so that is the difference I will be getting. The first line will be coming at 2b bar, next line will be, so 2 to 6, so difference again will be, in this case will be 4. Okay. The next will be 6b bar and so on and so forth. So, what happens is the spectrum will be a set of equally spaced lines. That is the kind of spectrum I expect from a rotating diatomic molecule, provided it is behaving as a rigid rotor. Let us recall for ourselves that we are talking about a model system, because our molecule is not rigid, we will come to that later on. Okay. So, we have assumed the molecule to be rigid. If that be so, then that is the kind of spectrum I am going to get. That means, for a rigid rotor, I am going to get a spectrum which essentially is nothing but a set of lines which are equally spaced, and the spacing happens to be of 2b bar. Okay. Now, if I want to just find out an expression, a generalized expression for the spectral lines, where do I get the, what is the position of spectral lines here? I can simply do it, that means that the nu bar, that means j to j plus 1 transition, that means the wave number of the transition from any level j to j plus 1 level can be computed by putting expressions for energy of j plus 1 level and subtracting from it the energy of the jth level. If it does do little substitution, I find the expression comes out to be 2b bar j plus 1. That means I can simply substitute the value of j here. Say when j is equal to 0, I get 2b bar, that is what I observed. J is equal to 1, I get 4b bar, and for 3, for 2 it will be 6, and so on and so forth. So, I will be getting the set of lines I just mentioned earlier. That means, I get the spectral lines at 2b bar, 4b bar, 6b bar, 8b bar, etc. So, what we have seen so far is that we have seen that if I take a molecule, a diatomic molecule, to be behaving as a rigid rotor, I will get some kind of an expression from quantum mechanics, the energy expression. That energy expression I can translate into energy level diagram, and then thereafter, using selection rule, I can work out what are the possible transitions, what kind of spectrum I get from there. So, what next? How do I use this spectrum? Now, basically what I have got as a spectrum is set of lines. To make use of it, let me just give you a small problem to be done. The problem is as follows, that is, if I take the rotational spectrum of carbon monoxide, the first few lines, this is experimental data I am sharing with you, they have been observed at say 3.845, 7.689 and so on and so forth centimeter inverse. The question is, what do I do with that? As I mentioned earlier, that is, the rotational spectrum can be used to calculate the bond length of the molecule. Let us see how does it happen. Now, let us first devise strategy to use this data. The first step of strategy is, that is, we must extract the value of b bar from the spectrum. We will see how do we do that. Thereafter, we use this value of b bar to compute the moment of inertia. The third step is we compute a reduced mass, and the fourth step is we obtain the value of r from the moment of inertia. All these relationships we have talked about earlier. Okay. Let us see how do we operate on this strategy. We start with the first step, that is extracting the value of b bar from the spectrum. What do? We just take consecutive lines which are observed on the experimental spectrum and take their differences. Say this is my second line minus the first one, that comes out to be 3.844 centimeter inverse. I keep doing, this is my third line, second and so on and so forth. When I subtract a given line from the succeeding line, I find that this difference comes out to be, and the average value of that happens to be 3.844 centimeter inverse. And we know that from our understanding what we just talked about earlier, that these lines are going to be at a space of 2b bar. So, that means this average value which I have got here represents 2 times the rotational constant, and from this I can compute the rotational constant, that is b bar, to be equal to 1.922 centimeter inverse. So, that is the first step. That means from the experiment, from the spectra which I obtained from experiment, I have got the value of my b bar, the rotational constant. Okay. That is my step 1. The next step is that I should be able to get the value of moment of inertia, and we will recall that our rotational constant b bar is related to moment of inertia by the following expression. That is the way we defined it, that is b bar is equal to h by pi square by 8 pi square I into c. So, what we do is we just rearrange the expression to get expression for I, that is moment of inertia, to be in terms of h and so on and so forth. We just simply substitute the values of h, pi, b bar, what we got in the first step, and the velocity of light c. What do I get? I get this value to be 1.456 10 to the minus 46 kg per meter square. So, that is the expression I get for my moment of inertia. That is my step 2. Now, we know that moment of inertia we defined that you recall that we did make a small derivation there, that I is equal to mu r square, where r is the bond length and mu is the reduced mass. So, having got the value of I, to get the value of r I must know what is the value of reduced mass. So, the next step is we compute the reduced mass, and by definition our reduced mass is m1 into m2 by m1 plus m2, where m1 m2 are the masses of particle 1 and particle 2, or in this case our atom 1 and atom 2. When I do that for our molecule, we have got carbon monoxide as a molecule. So, we put the masses of carbon and oxygen here, and we get the value of reduced mass to be equal to 11.38365 into 10 to the minus 27 kg, whatever it is. Okay. So, you get the value of mu by substituting the masses of the respective atoms constituting the molecule. So, once this is done, we are ready with our the final step, that is to compute the bond length. So, if, as I mentioned earlier, our I is equal to mu r square. So, I can just rearrange and get r to be equal to square root of I by mu. I have computed I have computed mu, I just simply substitute. When I substitute and simplify, I get r to be equal to 0.1131 nanometers. So, what we can conclude from here is that the bond length of carbon monoxide molecule as determined from the given rotational spectrum happens to be 0.1131 nanometers. So, that is the utility of what we discussed so far in this session, that is the spectrum I get here, the nature of spectrum, that is the equispaced lines there. So, that thing we are going to make use of to find out the bond length of the given molecule. Okay. Let us quickly sum up what we have done today. What we have done today is we have defined rotational spectrum and outlined the scope and significance, that is in terms of what do we do with the spectrum. If I get a spectrum, what kind of things what kind of information can I get about the molecule. Thereafter, we took rigid rotor as a model for rotating diatomic molecule. We will come down to that, that is not a correct model, we will come down to that in the next session. Thereafter, having considered rotating diatomic molecule to be rigid rotor, we kind of indicated what is the energy expression we get from quantum mechanics and the corresponding energy level diagram. Thereafter, we outlined the prerequisites and the selection rules for a rotational spectrum to be observed. And thereafter, we explained the nature of spectra which are obtained rigid rotor, that is we get a series of lines which are equally spaced. And towards the end, we took an example to show that how can the rotational spectrum be used to find out the bond length of a simple diatomic molecule. In the next episode, what we will try to do is, we will try to see that I have been mentioning again and again that we are using rigid rotor as a model. So, we will try to come to the real molecules. The real molecules, as I mentioned earlier, they are not rigid, they are non-rigid, they are vibrating. So, what happens if the molecule is not rigid? So, how does our energy expression get altered? How does our energy level diagram get changed? Accordingly, what happens to the spectrum? So, how do we make use of this? This we will be taking up in the next session. Thank you.